Hello, and welcome to this video on tabular Q-learning, where we will learn one of the core algorithms of reinforcement learning. Here we have our example of the mountain car environment. Our agent is supposed to steer this little car to the goal at the top of the mountain. For this, the AI has to learn a policy pi, which returns for each state which actions the agent will choose. To be more general, we allow here a distribution over actions, conditioned on the state. Since we know now which actions the agent will choose in each state, we can compute expectations over all possible futures. I'm using here the notation expectation of pi, which is the average over all possible future trajectories the agent can take. Our mountain car lives in a continuous world. Both the position and the velocity can take any number within some reasonable bounds. However, it is hard to specify the policy this way, and we will instead discretize the state space into a fixed number of states. This allows us to define the policy in each state as a number of states times number of actions table. Here on the bottom right, we have an example where the agent moves to the right in all yellow states and to the left in all purple states. This comes, of course, at a price, as a finer discretization allows for finer control, but also takes longer to learn. In reinforcement learning, we want to find a policy that maximizes all future reward. For this, we define the value function of a policy as the expected sum of all discounted future rewards. We need the discount factor gamma to make sure the sum does not go towards infinity. To represent the value, we use a table with the same state discretization as the policy. Here in the bottom right, we see the value of a very good policy, where blue is low and red is high. Now, we can reformulate this definition by taking out the first reward R0. Note that the remaining reward from R1 to infinity is still an expectation over the entire future, just starting from the next state as 1. We can therefore replace it with gamma times the value of S1. This is cool. It allows us to formulate the value as the recursive Bellman equation. A function that fulfills this equation will tell us how much reward we can expect if we follow the associated policy. However, we want to know which policy will give us the largest value. For this, we need to do a bit of math. Don't worry, it looks worse than it is. We start with the value function of a state S, but this time we want to find the policy pi that maximizes it. The first decision, A0, should maximize all future rewards, so we can simply put the maximum outside of the decision. The remaining expectation conditioned on both the first state S and the first action A is called the Q value, and we will call the Q value of the maximal policy Q star. Next, we can replace the infinite sum with the recursive Bellman equation. Note that the first reward no longer depends on the policy, and we can therefore move the maximization inside of the expectation. Technically, this step is a bit tricky, but just believe me that this is a legal substitution here. The last step uses the same trick as above. The next action shall maximize the future rewards starting from S1. And we put the maximum again in the front. Note that the remaining expectation is the Q value Q star from above, but from the starting state S1 and the maximal action A dash. This derivative allows us to define the optimal Q value Q star in another recursive Bellman equation. A function that fulfills this equation tells us, therefore, how much reward we can expect if we follow the optimal policy. This is kind of magic, because we do not need to know the optimal policy to compute Q star. However, if we know Q star, we get the optimal policy pi star for free. We simply always choose the action that has the largest optimal Q value with a probability of 1. If you didn't get it the first time, pause the video here and think a bit about it. Now, let's turn the math into an algorithm. This algorithm will learn the optimal Q values for all states using only interactions with the environment. We first create a table of the Q values with one entry for every state action pair. For every transition in the environment, we update the table entry of the corresponding state action pair using the right-hand side of the optimal Bellman equation. However, because the transitions can be stochastic, we don't want to override the table entry completely. Instead, we use temporal averaging and remember a combination of the old entry with the Bellman equation, weighted by some learning rate alpha. And when we rearrange the terms here, we see that this is the same as adding the scaled so-called temporal difference error to the table entry. And that's it. Here's some Python code of the algorithm. Every iteration of the while loop picks an action, executes it in the environment, and updates the table entry. Using this extremely simple algorithm, the table will converge to the optimal Q values, but only if we visit all state action pairs often enough. This is called exploration of the environment, and I want to finish this video with two very simple examples. The easiest way to ensure exploration is to simply choose random actions every now and then. This is called epsilon greedy, because we act random with a probability of epsilon and follow the greedy optimal policy with a probability of 1 minus epsilon. As there is a non-zero probability for every action sequence in this scheme, the entire state action space will therefore be explored eventually. However, if this takes too long for you, you can use a technique called optimistic initialization. Here, we initialize our table with an upper bound on the Q value. Because of this initialization, the TD error is always negative, and we will always overestimate the optimal value. This makes actions we have not seen, at least not very often, more attractive, but also stops the exploration if a Q value falls below the optimal value in that state. The agent will therefore explore until all overestimated actions fall below the optimal one, at which point exploration stops and the agent will have found the most rewarding policy. In summary, in this video, we defined the agent's behavior with a policy. We defined that policy's value and derived the optimal Q value function. We've shown that the tabular Q learning algorithm estimates that function with a simple update rule. And we discussed how we can guarantee enough exploration to converge to the optimal policy.